Okay, hopefully if you're still here, you're interested in VFIO. Jon Snow's probably the more entertaining talk, just fair warning. um, so let's get started. I always like to start with a quick introduction of VFIO in case you're not very familiar with it. This is a slide from my 2016 KVM Forum presentation. So if you want an overview of how VFIO works, please go look at that. Real quickly, VFIO is a kernel driver that decomposes a device, all the accesses to a device, into a file descriptor API where user space drivers can then make use of that device. And QEMU in particular is a user space driver that recomposes that file descriptor API back into a virtual device backed by a physical device. So some of the key components of VFIO, we start with containers, groups, and devices, where a group is defined as the minimum set of devices that are isolated from all other devices based on things like IMMU isolation and isolation between the devices. We add that group into a container. The container represents the IMMU context. Once we have that group protected by an IMMU context, we can then access devices. The device presents a file descriptor where the file descriptor is broken into regions, essentially just segments, where each region represents some aspect of the device. For instance, a PCI device, the PCI bars are mapped through regions, the config space mapped through regions. If it's a VGA device, it might have a region mapping that. Not shown here, event FDs are also used for configuring interrupts to devices. And then moving back to the container is how we program DMA to the device. So we map IO virtual address spaces that pin memory in the host system, map it through the IMMU, and allow the device access. We do that based on a group level, so you can't split IOVAs separate between devices and groups. So what we intend to talk about here today is what we've been doing for the last few years, things that I think are important for the community at large to understand about how VFIO is changing. So we're going to talk about live migration, variant drivers, and IMMU-FD. So live migration is often seen as one of the gaps for VFIO, where you get the highest device performance, but you tie your VM to a single host or a single device even. So there's been various talks over the past KVM forums about how to implement this. We started out with a version 1 protocol, which was based on a region interface. So we selected one of the regions of the device and had essentially the driver for the device indicate how to interact with that, performing reads and writes to do device save and restore. We didn't place any restrictions on device state transitions, which became a problem. And it was never adopted by any in-kernel drivers. So it was only the out-of-tree NVIDIA kernel that ever used this. So when drivers came along, they wanted to implement an in-kernel driver. We decided this was too complicated and removed it. So for the rest of the presentation, we'll be talking about the version 2, which is the current one that's now upstream, which is more of a streaming protocol. So you get a new file descriptor when you enter or and invalidated when you remove sessions for saving and restoring devices. So it's much easier to work with. You just read and write from the file descriptor. And we've streamlined the state transition, so we don't allow arbitrary state transitions. We go through defined arcs, which makes things easier for the drivers that need to support this. So in the most basic, minimal state diagram for migration, we enter a device into the running state for compatibility with non-migrating devices. From there, we can go to a stop state and enter either the stop copy state for saving the device or a resuming state for setting the device state. So each transition into or out of these, as I've represented here, a green or blue box, that represents getting a new file descriptor, and when you leave that session, it's invalidated. We're dealing with physical devices, and any transition might generate an error. So everybody has a dotted line to an error state where to exit that error state, you have to reinitialize the device, put you back in the running state. But also, since we're dealing with real devices, they do peer-to-peer DMA between devices, potentially. We don't have an atomic way to stop all devices at once. So we introduce an optional peer-to-peer support where a device is required to accept incoming DMA, but cannot generate outgoing DMA. So by moving all of the devices into this state, we know that the system is quiesced, and then we can move things to the stop state and continue normally. But also, as we saw in the multi-FD presentation yesterday, devices have a lot of state. So we can't rely only on a stop copy implementation. So we need pre-copy support, and when we integrate pre-copy and peer-to-peer support, we get multiple states within this saving session and new entry and exit points from the saving session. So typically, you would go from a running state to a pre-copy state to a pre-copy peer-to-peer state to a stop copy state. And so the color coding here is meant to indicate red is the pre-copy states, red is the P2P states, yellow is the pre-copy states, and then orange is required when you have that overlap between them. Pre-copy also requires some initial, way for the driver to indicate initial bytes for indicating that the target VM is ready to go and can reduce the latency of starting up the target VM, and also dirty bytes ongoing because the device continues running and continues dirtying state. So that covers the device itself, but the device can do DMA. So the device is potentially perpetually dirtying memory for the VM. And it can do so quite rapidly. With new devices, we have potentially bandwidths of 128 gigabytes per second. If we don't have a way to track the data that a device is writing to, then we have to assume all memory that it has access is dirty, which is obviously untenable. So we introduce some new interfaces for the VFIO device that allow the driver to expose a device-level dirty tracking support, where QEMU can specify an IOVU range to track, and it gets a dirty bitmap that is incorporated into the CPU dirty bitmap. So status for migration, the MLX5 and the HiSilicon ACC driver, which is a crypto device, were the two that came along that really proved out this V2 implementation. And that went into the kernel in 5.18. AMD PDS is a network driver that came along in 6.6, and more recently, Intel QAT was added in 6.10. And of course, the NVIDIA out-of-tree driver also supports this new interface. As far as QEMU goes, V2 migration support was added in 8.0, along with dirty tracking support. Pre-copy came about in 8.1, and P2P support, which enables multiple devices for migration, came about in 8.2. So obviously there's a question of where does all this code live? Because we can't continuously expand vfio-pci for every new device. So the refactoring that's been done here is that we've taken vfio-pci itself, split it out into a core driver, which becomes a library for what we're calling variant drivers, variations of the vfio-pci driver. So the vfio-pci module becomes much slimmer because it uses that core module, and it becomes the de facto variant driver. Then we add a new variant driver for each one of these devices supporting migration. So we have an MLX5 driver, an HiACC driver, a PDS driver, and a QAT driver. But migration isn't the only case where we need variant drivers. We also have some interesting other in-kernel drivers that are variant drivers. NVGrace is one of those, where it's a device that when the system boots up, it switches from using the PCI bar directly to using a coherent memory range. And this driver actually presents that coherent memory range as if it were the PCI bar for the device. There's also an interesting device, a VirtIO vfio-pci device, where here we have a physical SROV virtual function that is a virtual NIC, a VirtIO NIC, And that device only presents a modern VirtIO interface to the guest, but there are requirements for presenting a legacy VirtIO device. So this driver works through the PF driver to be able to modify what's exposed to the guest to present that legacy VirtIO interface. So as we add new drivers, we have to deal with how does user space select the correct driver for a device. And for that, we leverage what's already done with kernel modules, making use of module aliases, things like the kmod utilities. So essentially, we take how a driver would typically expose the set of devices that it supports, where it provides an alias, where there might be wildcards in that alias. Here we're showing some examples where vfio-pci provides full wildcards, while the MLX5 provides a vendor ID and a device ID. Same with the PDS driver. So user space essentially needs to go through the aliases for a device and pick the one that's the best match. And this has already been added to libvirt. So if you have a managed equal yes device using libvirt 10.0, then libvirt will automatically go through and find the most appropriate driver for the device. Also, with the introduction of variant drivers, there's a question of what happens to MDev. MDev is how we started out doing things like vGPU, and it's still used by Intel vGTG, as well as CCW and AP devices on S390X. MDev still exists. It will continue to exist. It seems like it's probably more appropriate when you're dealing with a purely software-defined device, whereas the VFIO variant driver would be more appropriate where you have some sort of IOMMU support for the device. In fact, for a while we had an interface in MDev for specifying an IOMMU backing device for an MDev device. Again, there were no in-kernel users of that, so that was removed, which really pushes things towards using a variant driver when you have that sort of scenario. As we transition from devices from using MDev to variant drivers, there are some hurdles. There are going to be different methods of configuring the device, and we don't have at least the MDev control tool for setting parameters and managing the lifecycle of devices. So that's something as a user you'll need to be aware of. Switching over to IOMMUFD, IOMMUFD is proposed to be a new subsystem for the kernel for doing user space IOMMU management. It overlaps a lot of functionality with the IOMMU backends of VFIO, but it tends to support more features such as page faults, error reporting, nested paging, passage support, etc. VFIO and VDPA are the intended initial targets for IOMMUFD. And given that overlap, we do eventually intend to replace the IOMMU backends of VFIO with IOMMUFD. So as a result of that, if you want new functionality in type 1, you need to get it into IOMMUFD first. And then if there is a sufficient need for it in the legacy type 1 backend, we'll consider whether or not to support it there as well. An important distinction with IOMMUFD is that it provides a device level interface rather than a group level interface. So this is just sort of the paradigm of the interface is groups are hard to deal with, and the device interface makes more sense, but the IOMMU group constraints are still there. So IOMMUFD kind of envisions a world where we have more singleton devices, singleton groups, where there's only one device per group. So we'd like to get to that. We're not quite there yet. So under the covers, you still have to deal with groups. So just looking at the flow comparison between the two, in the VFIO API, as I showed earlier, you start with a container and a group, and you set the container for a group, which establishes the IOMMU context for the group, the protection domain essentially, and then you have access to the device. And the IOMMUFD API, we kind of turn that around. You start with a device and an IOMMUFD, which is an instance of opening the IOMMUFD file. That allows you to bind the device to the IOMMUFD, and therefore you can create IO address spaces, IOASs, within that IOMMUFD. Um, you can then attach the device to the iOS, which again then makes the device fully accessible. So as you may have figured it out, this requires yet another new interface to vfio where we actually need to be able to access the device rather than the group. So we create a new character device interface um, where we can access the device. So you can find this through sysfs. And like VFI, it's essentially a stub device until you map it into an IMMU context, or at least have a blocking domain around that IMMU or for the IMMU. But once you establish that, then you can get access to the device. You can use the legacy interface and the new interface at the same time, but not across the same group. And this was added in Linux 6.6. So a few notable features of IMMUFD. The VFIO container model, each container has a separate IMMU context, and they don't talk to each other. And that gave us a problem with page pinning between those containers. So if you pin a page in one container, another container doesn't know about it, and we end up with duplicate accounting of that pin paging. IMMUFD solves that problem because we have a single IMMUFD instance, and you can have multiple IOASs, multiple address spaces within that IMMUFD. So IMMUFD knows about all pinning within that instance of the IMMUFD. Therefore, we won't have to set exceptionally large locked memory limits when we're running VMs with IMMUFD. Also, the way we had modeled devices in groups made it difficult for libvirt to pass file descriptors to QEMU for managing VFIO devices. It was always a question of, does VFIO need a new container for a device or not? Since we have multiple IOASs within an IMMUFD instance, and we can now access the CDEV directly, we should be able to return to a model where libvirt can use SCM rights to pass file descriptors when instantiating a VFIO VM. IMMUFD also provides a compatibility mode. So simply by linking the VFIO container file to the IMMUFD file, it behaves as if it is a VFIO container. So that should ease transition as we move to IMMUFD. And also going back to migration, one of these advanced features that IMMUFD intends to provide is dirty page tracking at the IMMU level. So hopefully we don't have the need for each migration device to support dirty page tracking itself, and we can make use of the IMMUFD hardware for that. Status of IMMUFD, as I said, we intend this will eventually replace the VFIO IMMU backends, but we've not officially begun that deprecation process. These compatibility interfaces I mentioned should ease that transition, hopefully making it largely transparent. But at some point we will switch over and hopefully be able to turn off those compatibility interfaces as well. There's still at least one feature gap that we're waiting to be fixed before we can begin that transition, where IMMUFD does not yet support peer-to-peer DMA between devices. So you can't actually map the MMIO of a device through the IMMU using the IMMUFD interface. Jason says that's an easy problem. Kernel support was added in 6.2. QEMU support was more recently added in 9.0. So now we have a new IMMUFD object for QEMU and a new parameter for the vfio-pci device where you can specify that IMMUFD object to use. I suppose we do allow multiple IMMUFDs to be created, but it's not really recommended for the reasons I mentioned with locked page accounting at least. libvirt support for this is in progress. Also a note, at Plumbers last week, there was a session on IMMUFD, and Jason Gunthorpe provided an overview of where things stand. I won't go over this in detail. You can look at his presentation for more details. But you can see there is quite a bit in progress. And even in the kernel that was just tagged last week, we've added fault delivery to user space. All right, so ongoing work. There's been some discussion about whether VFIO should be taking config space from the device or building it itself. The argument here is that, especially if we get to the point of having VirtIO devices that are manufactured by different vendors, they might be compatible but have different PCI config layouts. And if the VMM were to build that config space, then we might be able to solve some of the problems that we'll run into otherwise with migration. There's been some proposals about exposing MMIO via DMA buffs, and that might actually be how we support P2P mappings through IMMUFD. There was also the talk yesterday about multi-FD migration. So these devices tend to have a lot of state, especially when you get into GPUs and 100+ gigabit NICs. They're essentially their own computer underneath anyway. And then also Ji Wang has just posted a series proposing introducing the NVIDIA vGPU support as an in-kernel open source driver. So that might be our next variant driver entering the kernel. So that's pretty exciting. And then, as I mentioned, there's all sorts of IMMUFD potential things to talk about. Nested paging, generic page tables, faults to user space, process address spaces. SVA support is under development as well. And also I'd like to point out Cedric Legautier is effectively, if you've been on the mailing list, you've seen that he is the acting VFIO maintainer for QEMU. So thanks to Cedric for stepping up for that. And I think that's all I have. So any questions? Way in the back?
So question about IOM-UFD, is there a way to subdivide the device, or you have to have the hardware providing a lot of devices?
Subdivide the device as in splitting groups?
Right, like the groups.
Yeah, so you're still under the IMMU, or you're still under the IMMU group constraints that you can only have all the devices within the group need to be within the same IOAS. To get around that, we need hardware support to make sure that there's not any isolation gaps between the devices. So you need ACS support in the IMMUFD, or sorry, in the downstream ports.
The VirtIO IOMMU backend that does the current legacy translation, that was fairly interesting. That means you can add any kind of device emulation behind it, just expose it as VirtIO, which maybe eases live migration a little bit. Has any thought been given to that?
Certainly, variant drivers open the door that you can implement more emulation in the kernel driver. I don't think we want to get into that point of providing arbitrary emulation. So in this particular case, the physical function of the SRV device provides a gateway to enable the legacy support.
How? Just bit fiddling, is that it?
Well, we have to change some of the PCI config space. We have to enable a virtual IO port space. That IO port space access goes through the physical function of the device. So the physical function has to expose capabilities in the VirtIO space.
Yeah, makes sense. Thanks.
Great, thanks.